So initially, the JVM acts like any other interpreter, running each line of code as it is needed. However, by default, this would make the code execution somewhat slow. Certainly, if you compared this to code written in a language like C, which would be compiled to native machine code. The way that this kind of language works is that the code is compiled into a runnable format that the operating system can comprehend directly. It doesn't need any additional software to interpret or run it. This makes it quick to run compared to interpreted languages. But using these kind of languages that are compiled natively means that we lose the write once, run anywhere feature of Java. So to help get around this problem of slower execution in interpreted languages than compiled languages, the Java virtual machine has a feature called Just In Time Compilation, or JIT compilation for short. The JVM will monitor which branches of code are run the most often, which methods or parts of methods, specifically loops, are executed the most frequently. And then the virtual machine can decide, for example, that a particular method is being used a lot, and so code execution would be speeded up if that method was compiled to native machine code, and it will then do so. So at this point, some of our application is being run in interpreted mode as bytecode, and some is no longer bytecode, but is running as compiled native machine code. The part that has been compiled to native machine code will run faster than the bytecode interpreted part. Just to be clear then, by native machine code, we mean executable code that can be understood directly by your operating system. So if you're running this application on Windows, part of the bytecode has been compiled into code that can be natively understood by the Windows operating system. If we were running on a Mac, then the JVM would have compiled this to native Mac code. The native Windows code and the native Mac code would of course be different. They're not compatible. So the Windows JVM is able to create native Windows code, and the Mac JVM is able to create native Mac code. This process of native compilation is completely transparent to the user, but it has an important implication. Your code will generally run faster the longer it is left to run. That's because the virtual machine can profile your code and work out which bits of it could be optimized by compiling them to native machine code. So a method that runs multiple times every minute is very likely to be just-in-time compiled quite quickly, but a method that might run once a day might not ever be JIT compiled. The process of compiling, converting the bytecode to native machine code, is run in a separate thread. The virtual machine is of course a multi-threaded application itself, so the threads within the virtual machine responsible for running the code, that is interpreting the bytecode and executing the bytecode, won't be affected by the thread doing JIT compiling. So the process of JIT compiling doesn't stop the application running. While the compilation is taking place, the JVM will continue to use the interpreted version. But once that compilation is complete and the native machine code version is available, well then the virtual machine will seamlessly switch to use the compiled version instead of the raw bytecode. Now, if your application is heavy on processing, using all of the available CPU resources, you could potentially see a temporary reduction in performance if JIT compilation is taking place, although it would only be in the most critical and high power processing applications that you might notice this, and even then it's going to be well worth the slight dip in processing power to get the benefit of the native code version for your method. One impact of JIT compilation is that if you're assessing the performance of a particular piece of code, you actually need to think about when you're going to do that assessment. Supposing you're trying to determine how long a process takes to run, and you want to see which of two alternative methods will run more quickly. If you assess the performance of these methods when your application first starts, you might find that you get different results than if you assessed it after your application has been running for a short while. You need to think about whether you're assessing the performance of the code before it has been natively compiled or after. We'll actually come back and consider this point in some detail later on in the course when we look at measuring performance. But as a programmer, it can be interesting to know which methods or code blocks are being compiled to native machine code. Actually, until this point, I've been really a bit vague here about what can get compiled to native machine code. The answer is any sequence of bytecode can be compiled. Now, from our point of view as programmers, we can think of this as meaning any method or any code block. It's not a completely accurate translation, but it is good enough to understand what's going on.